What we're talking about here is conformations of butane, which has more conformational possibilities than ethane does. And in fact, we have 4 different conformations, and what we're doing here is going over them in order from lowest energy to highest energy. We'll write them out first, then we'll name them, then I'll show you what they look like, if I can, God willing, with the document camera, because I've got a molecular model here that I can show you what they look like. And last but not least, we'll draw the energy diagram. So that's the order that I want to do this in. So this is the lowest energy conformation of butane. I'll even write lowest energy over here. Thanks for keeping an eye on me in chat, by the way. Good. So yeah, luckily we hadn't got too far in. That's going to be the lowest energy conformation, and I think you can see why. These 2 methyl groups, which have the most electron density around them, right? They've got these 3 CH bonds. And we started to talk a little bit about torsional strain the other day, and we'll talk about it more and we'll define it several times over. But torsional strain is essentially an increase in energy that you get whenever electrons in bonds are closer to each other in 3-dimensional space than they need to be. And I think you'll agree with me, we can't get those 2 methyl groups any further away than that. That's as far away as we can possibly get them. So that's going to be one of our eclipsed conformations. We're going to wind up calling that the anti-conformation. I'll write that down in a little while. We're going to draw the structures first using Newman projections, then we'll name them. The next lowest energy conformation is still going to be staggered. However, the methyl group on the back carbon is going to be only 60 degrees away from the methyl group in front. Right here, it's closer than over here. And so the electrons in those bonds, that's the main thing that you need to know about torsional strain. It always has to do with electrons in bonds, the repulsion of electrons in bonds. Right? Electrons are negatively charged, like charges repel. And so if you're getting negatively charged things closer to each other than they really need to be, there's going to be an increase in energy. It's going to be less stable. Does that make any sense? And again, I've put the definition of torsional strain in the class notes. That's all in there for your perusal. So that's a different staggered conformation. It's still staggered, and I think I might have said this wrong before. Both of those are staggered. The way you know that is because nothing's directly in front of and behind of each other. Right? Do you see they kind of look like the ethane staggered? So they're both staggered, but this staggered is lower in energy than this one, and so we're going to need different names for that. The next higher energy conformation is going to be eclipsed, but at least it's not the 2 methyl groups that are eclipsing. At least each methyl group is getting eclipsed only by a hydrogen. So maybe something like this. And incidentally, these Newman projections do not have to look exactly like that in order to be correct. You can turn them, you know, they can be turned any which way. So that's going to be the next, that's going to turn out to be the second highest energy conformation. And last but not least, the highest energy conformation has both of the methyls eclipsed, and that's a little tricky to draw. Good. So those are they. And since we have 2 different eclipsed conformations and 2 different staggered conformations, we need names for all of them. So this one we call the anti-conformation. We only use the word anti in cases like butane, where there are different eclipsed and different staggered conformations. This one we call gauche, G-A-U-C-H-E, or I've also heard it pronounced gauche. I don't really care which pronunciation you use. This eclipsed conformation is different from that eclipsed conformation. And for this, you might want to call it something like the hydrogen methyl eclipsed or methyl hydrogen eclipsed. And between the H and the CH3, you can use a slash, you can use a dash, you know, anything you want to separate those 2 is perfectly fine. And this one we will then want to call the methyl-methyl eclipsed. That's going to be the highest energy conformation. Well, we'll get to that in a moment anyway. So let me, for the purposes of giving you somewhat more visual aids, this will still be on the whiteboard. And incidentally, you could possibly be watching this on YouTube or something like it from the other class and stop it so that you have time to copy all of that down. But that will be available. So here we are looking down the C2-C3 bond. And I think you can all see that this methyl is in the front is pointing up, and this methyl in the back is pointing down. That's what it means when you draw that Newman projection. That's what it refers to. It's not just a picture to memorize. It means this. It's a way of depicting this. And I think you'll agree that these two methyl groups on the ends are 180 degrees apart. So that's the furthest we can get them away from one another. Meanwhile, if we turn it 60 degrees, we run into an eclipsed conformation. In this case, it's a methyl and a hydrogen that are eclipsed. And then another 60 degrees. That now is a gauche conformation. The way I know that is because it falls into the definition of staggered, but these two methyl groups on the ends are closer together than they really need to be. Another 60 degrees, and now the two methyls are eclipsed. That's the lowest energy conformation. 60 degrees past that, and you've got gauche. Another 60, and you've got the methyl hydrogen eclipsed again, a different methyl hydrogen eclipsed, but same energy. And then another 60 degrees, and we're back to anti. So that brings to mind another minor thing maybe. Your book seems to be, or not, your book doesn't do anything. The authors of your book seem to be of the opinion that 0 degrees has to be defined as a particular thing. I don't see why that needs to be true. You can define whatever conformation you want as 60 degrees. And you can then turn in 60-degree increments. And you can think of that, and you can start wherever you like when you draw your energy diagram. It doesn't have to be defined as a particular thing. However, once you pick a starting position and call it 60 degrees, each 60 degrees after that is going to be defined as something in particular. So I'll show you what I mean when we draw this energy diagram, which is coming next. God willing, and the creek don't rise. Good, so how do we show all that then in an energy diagram? We need to depict somehow that there's 4 different conformations, two eclipsed and 2 staggered, and the lowest energy is this anti, and then the highest energy is eclipsed, and we need to reflect what we've done up till now. If we start, let's say, in the methyl-methyl eclipsed conformation, another 60 degrees and we've got a gauche, another 60 and it's methyl hydrogen eclipsed. And we need to show, relatively speaking, just qualitatively, what those relative energies are. So the energy diagram will look not entirely different from the one with ethane. So the main phenomenon going on here is going to be torsional strain. Later today, we're also going to get to angle strain, and we'll define that as well. As I said, steric strain is a third thing that is somewhat more general than torsional strain, and we'll talk about that probably a fair bit over the next 2 classes. Okay, so what are we going to do in terms of our energy diagram? Oh, that reminds me of another thing. The authors of your book seem to feel that 0 degrees of dihedral angle is strictly defined as one particular conformation. I don't see why that is. In fact, I don't agree with that. There's nothing that defines 0 degrees as being a particular thing. Degrees themselves are defined, right? A 60-degree turn means something in particular. And each turn of 60 degrees around that central carbon-carbon bond is going to give you another conformation than what you started with. But I don't know that 0 has to be defined as anti or defined as methyl-methyl eclipsed or anything like that. In other words, you can shift the energy diagram horizontally to whatever extent you want, and it will still carry the same information. The point being for you guys in terms of what you need to know is you don't need to memorize that 0 degrees means something. Does that make sense? It doesn't necessarily mean correspond to a particular conformation. At least I don't see why it should. Okay, let's see if we can manage to get our document camera to work, because I want to show you these before we go on to, yay, before we go on to our energy diagram. So let me make sure we're looking directly onto that carbon-carbon bond. Yep. So there you go. That would be the lowest energy anti-conformation. The methyl in front is 180 degrees away from the methyl in back. When you turn 60 degrees, you get one of the eclipsed conformations. So the energies don't go in order, lowest, second lowest. It doesn't go like that. The next conformation, you can tell by looking at it. Here's a hydrogen, here's a methyl. Here's also a hydrogen, or rather, here's also a hydrogen, here's also a methyl. So this is a methyl hydrogen eclipsed conformation. The way you can know is by looking along the bond and seeing that it's a methyl and a hydrogen that are eclipsing rather than both methyls. But we're still looking down that central C2-C3 bond. These glasses are not working. So far, so good. Another 60 degrees, and what do we get? Well, this is now staggered again. The way you know is because this falls under the definition of staggered that we gave a class or two ago, because nothing is eclipsing anything. But I think you'll agree, these two methyl groups are closer in space by a lot than they were in the anti-conformation. This is the Gauss conformation. 60 more degrees, and you've got the highest energy one, the methyl-methyl eclipsed. 60 degrees past that, you're back to Gauss. 60 degrees past that, you're back to methyl hydrogen eclipsed. Another 60, and you're back to anti. So molecular models can be helpful in terms of visualizing all this. But how would we show that in an energy diagram? Well, we would do it something like this. So here's our, wait a minute, am I sharing the whiteboard? I'm not sure that I am. Looks like I am. You guys can still see the whiteboard in chat, right? Good, I just wasn't sure. So I feel like putting the methyl-methyl eclipsed conformation first. I feel like defining that as 0. It doesn't have to be that way, but we'll just start there. We'll just arbitrarily make that our starting point. Oops. And again, you can write either CH3/CH3 or CH3-CH3. As I said, I've even seen a couple other punctuation marks used. So that's going to be the highest energy one. And remember, after the methyl-methyl eclipsed, when we turned 60 degrees, we got a Gauss conformation. That's going to be the second lowest energy, rather. Then another 60 degrees, and we got a methyl hydrogen eclipsed. That's going to be somewhere intermediate in energy between methyl-methyl eclipsed and Gauss. And then another 60 degrees, and we got to the lowest energy conformation, the anti-conformation. Another 60 degrees, and then we were back up to a different methyl hydrogen eclipsed conformation, but still same energy as the other. Another 60 degrees, we're back to another Gauss. And then last but not least, at 360 degrees, the same as 0. We're back up to methyl-methyl eclipsed. And so, carefully trying to draw this shape, it's still very similar to a sinusoidal type shape. It's just a little bit more, whoa, that sucked. Sorry, but I call it like it is. I saw one of these types of energy diagrams online when I was doing a search, and it made them like straight lines like that. I'm not a fan of that. I don't think it's straight lines. I think it's more like a sine type shape. Except it's probably not going to work. Oh, wait a minute. I know what will work if I make it white. Ooh, maybe a little better. Maybe not. Good. So, so this would be a correct way of drawing the energy diagram for butane. It's kind of similar to that of ethane, except again, we have to reflect that there's two different staggered conformations and two different eclipsed conformations. Now, all of these energy differences are known. I don't have them memorized. I have them in my notes. I sure wouldn't expect you to memorize them. Looks like the difference between anti and gauche is 4 kilojoules per mole. Between anti and methyl hydrogen eclipsed is 16 kilojoules per mole. And if we've got any calories people in the audience, you can just divide by 4.184 and you'll get it in kilocalories per mole. And then the distance between, or the energy difference between anti and methyl eclipsed is 19 kilojoules per mole. I'm a joules man from my years of teaching Gen Chem, and at least under normal conditions, I do research over the summer with Dr. Daniel Singleton and his group. I'm not a research professor, but I am associated with their group, or at least I try to be, and they do everything in calories, and they always make fun of me. Oh well, it's just a burden I have to put up with. Good, so those are the energy differences, and as I said, if we wanted to, we could use that and calculate how much of each of those conformations is present in a sample of butane at any given time. I'm not really interested in doing that. My goal for any given organic chemistry exam is to make it so you don't even need a calculator, and I think in general you won't. If you want to bring like a little 4-function calculator just in case, you know, I would feel pretty terrible if someone lost points because they, you know, couldn't add or something like that. I would feel pretty bad. So, but in general, I don't expect you'll normally need a calculator. So that tells you whether you can see, whether you can expect to see delta G equals delta H plus D delta S type questions. Good, but I think that's basically it. We're at a little past 12:30. I have till 12:50. Good. Questions on that energy diagram then? Yes. Sorry. Looks like it's 3 kilojoules per mole, right? Because 16 and 19, at least assuming I copied all that down correctly. And again, I really don't care if you guys memorize those numbers. Please don't. I should mention, just like there's many molecules that behave like ethane, there's also many other molecules that behave like butane. You can replace both of those methyl groups with OHs. Call that molecule ethylene glycol, and you'll find that in antifreeze. Behaves very similarly to butane, except I guess instead of methyl hydrogen and methyl eclipsed, you'd have OH hydrogen and OH eclipsed. You can replace them both with chlorines. Call that 1,2-dichloroethane. You can probably name that already. Very similar molecule in terms of its behavior. And again, the only thing I'd expect to change would be those exact numbers of the differences in energies. But I would expect the energy diagram to look real similar to that of butane. So that's about all we've got time for in terms of chapter 3. Again, I wish I could cover every single topic with multiple examples of each, but we have to move on. We have to start chapter 4. But I think at least we've covered the things that in my experience need the most explanation. So any last questions before we go on to chapter 4? Anything in chat? Anything from, I don't know that they use this term still. They used this sort of, unpleasant term for occurring in real life about a decade ago. They used to contrast like the web or the internet, and in contrast to that, in real life, you've got meat space, like MEAT, meat. I don't know if they still use that term. It's a little bit unpleasant. Anyway, good. Let's clear all that off. and we'll get ready to move on to cycloalkanes. What can we say about cycloalkanes by way of introduction? Well, I think you've already seen examples of structures that have rings in them. It's just a pretty common thing. And not just benzene, there's also saturated hydrocarbon cyclic compounds. And 5- and 6-membered rings especially show up a lot in natural compounds. I'm thinking here of steroids and sex hormones and things like that. You've got 5- and 6-membered rings, all kinds of different drugs. We could go on and on. These things show up a lot. And so we need to know something about what the structure of cycloalkanes is like in order to understand some of these larger molecules better and why they do what they do. In terms of naming cycloalkanes, I think, again, the best I can do for you is to leave you to practice that on your own. I would say if you know how to name acyclic alkanes, that will probably, no lie, be at least 95%, maybe even 97, 98% of what you need to know in order to name any cycloalkane. The main difference, of course, being that cycloalkanes, well, are cyclic. And so you don't have the two ends of the molecule. You're not going to be numbering from one end to another. There is no end in a ring. So that's the only difference. It modifies the rules just slightly. But you've got lots of opportunity to practice naming cycloalkanes on OWL. So there's some good questions there. At least I hope there are. There were some bad questions too, but you should never even see those. By the way, just in case you guys are wondering, in a typical OWL EOC assignment, I try to make it somewhere between 10 and 20 questions, but it might be that they give me 35 or 40, and I throw a good number of them out, especially if there seems to be anything wrong with the question. So I have vetted it to some extent. I've tried my best to get rid of any, truly awful questions. Okay, so all that being said, cycloalkanes. I think you'll agree that in order to get a cycloalkane, it's sort of common sense. You need at least 3 carbons. There's no such thing as a 2-membered ring. You have to have at least 3. And so the smallest possible cycloalkane would have 3 carbons, and so we would, of course, call that cyclopropane. And cyclopropane is known. It does exist. It is also exceedingly strained. And torsional strain is not the main problem here, though there also is a significant amount of torsional strain. It turns out all of the hydrogens in the whole molecule are eclipsed and can't get away from being eclipsed. But that's not the main problem. The main problem is the bond angle here. So that bond angle must be 60 degrees by definition. Those 3 carbons have no choice but to form an equilateral triangle. So as a result, the bond angle must be 60 degrees. Well, what should the bond angle be? Well, the way we know that is we first observe that all 3 of these carbons have nothing but 4 single bonds around them. And you need to know that a carbon atom with 4 single bonds is sp3 hybridized. And what's the ideal bond angle for sp3 hybridization? Hopefully you all remember, the ideal bond angle is 109.5 degrees. And not every single sp3 hybridized atom is always exactly 109.5, but it certainly wants to be pretty close to that if it can be. And 60 degrees is nowhere near close to 109.5. So that introduces a kind of strain or energy increase into the molecule. This type of energy increase we call angle strain, and it goes by 1 or 2 other, you can call it ring strain also, but it's another type of loss of stability or increase in energy. And you find that whenever our bond angles are at all significantly far away from the ideal bond angles, which is 109.5 degrees for sp3, 120 for sp2, 180 for sp. Anything that forces the molecule, significantly far away from those ideal bond angles will result in an increase in energy. And so in cyclopropane, that's particularly bad because we're at 60 degrees. That's very, very exceedingly compressed compared to 109.5 degrees. What about the next one? The next one, cyclobutane. I think you see already how naming these things goes. It's tempting to draw cyclobutane as a square, and you can. It's not wrong. As a flat structure, it's perfectly fine. But as it turns out, cyclobutane is not planar. It's not the shape of a perfect square, but rather it puckers out of the plane a little bit. Try to draw this. Something like that, maybe. I'll show where the 4 carbons are. Something like that. I'm probably exaggerating it slightly. But the real structure of cyclobutane is something a little more like that. And so this bond angle turns out to be a little more than 90 degrees. It's maybe like 94, 95, 96 degrees. It's a little better than if it were a perfect square, but still a significant amount of strain, still pretty far away from that ideal bond angle of 109.5. So cyclobutane is also quite strained. Not quite as bad as cyclopropane, but still quite a lot of angle strain. Yes? Kind of, yeah. Something like that. Yeah, the molecule isn't planar, so those are where the 4 carbons are. I mean, I'm exaggerating, I think. They probably did a better job in your book. As I recall, they did a better job in your book. But I'm just trying to express, the question is about the shape of cyclobutane. Just as long as you're all aware that it's not planar, it's not a perfect square. So that's cyclobutane. And I should mention, the amount of strain in the molecule can be expressed quantitatively. In your book, you'll find a table that expresses something like the heat of combustion per CH2 in the molecule. Because you need to do that, you need to correct for the number of carbons in the molecule. Otherwise, you're not comparing apples to apples. You know, you can't directly compare cyclopropane to cyclobutane with something like heat of combustion, because cyclobutane is 1 more carbon than cyclopropane. It's not comparing apples and apples. So that's what that table is trying to express. Of course, I don't care if you memorize all those numbers, but what you'll see I mean, certainly take a look at that table, and I think you'll be able to convince yourself that cyclopropane is by far the most strained of these cycloalkanes. Cyclobutane still pretty strained, not quite as much as cyclopropane. You will find that in cyclopentane, there's a little bit of strain, but very little, very, very little. It's almost free of strain. Cyclohexane is completely free of angle strain. And that's why we're going to be spending so much time on cyclohexane. That requires its own lecture or two. And interestingly, as you add more carbons past cyclohexane, as you go to cycloheptane, cyclooctane, all those things are known. You know, they've all been made and studied. But as it turns out, adding more carbons past 6 makes things worse, because you wind up with the molecule folding such that some carbon is always bumping into some other carbon. And you wind up with a fair bit of steric strain. There you go. So we'll talk more about steric strain probably over the next 2 classes. But cyclohexane is special, and that's why we have to take a significant detour with cyclohexane. Good, so much for cyclobutane. Cyclopentane's next. And sure, you can draw it like a pentagon. That's fine. It's perfectly acceptable. But as a matter of fact, a cyclopentane isn't shaped like a perfect pentagon. It's not planar. Like cyclobutane, it buckles slightly out of the plane. Let me see if I can quickly build a cyclopentane for you guys. And these modeling kits can be a fair bit of help, at least I think. Let me see now. The foot bone's connected to the leg bone. There we go. So let me go back to my document camera, and we'll see if we can see it in all of its glory. There we go. Let me just move that a little bit so it stays on camera. And I'm trying to show it here, but you can sort of see there's a bit of a kink over here. All 5 atoms are not lying in the plane. And so as a result, cyclopentane does have some conformational flexibility, not to the degree of cyclohexane. And the strain is not zero, but it's pretty low. Those, if you look down any one of these bonds, those hydrogens are almost staggered. Not quite perfectly so, but almost. So cyclopentane has very low strain, not zero, but very low. Cyclohexane is when things get interesting, as I said. So good. I think that's about, I do want to go over, I think I have time to go over, yeah, I still have 4 minutes. So that's going to be enough to go over the cis and trans phenomenon in cycloalkanes. Good. Make sense? Yes. The question is, why is there low strain in cyclopentane, at least I think. Yes, the reason is the bond angles have now moved pretty close to 109.5 degrees. Not perfect, but it's very close. It's not like 95 or 60 for sure. So the reason is there's now enough carbons that you can get pretty close to the ideal bond angle. Well, I'm saying the molecule's not planar. One of the carbons is going to be puckered out at any given time. And that actually lowers the energy somewhat. The reason the molecule does anything is to lower energy. So it would be higher energy if it were planar. So it puckers a little bit out of plane. That's going to be even more dramatic with cyclohexane, which we'll get to starting on Friday. But did I answer your question? Okay, just want to make sure. Good, how are we doing in chat? We use the modeling kit very often. Yes, oh, yeah, we're going to do axial and equatorial, all that fun stuff. Good, so there's just one other phenomenon that I want to make you guys aware of. I've already heard a lot of you talking about cis and trans alkenes, and that's great. We'll get to that eventually. We'll also get to what happens when the cis-trans system with did I say alkane? I meant alkenes. But there's places where the cis-trans system in alkenes breaks down, and so we'll take care of that too. But the term cis and trans can also be used with cycloalkanes. Let's sort of take a cyclopentane, and I'm going to kind of draw it on its side, sort of. And let's consider, I don't know, maybe 1,3-dimethyl cyclopentane. It turns out this molecule has 2 isomers. Actually, it might even be a little more complicated than that. That's one of them. And the other one, let me maybe bold these so it looks more like we're turning it on its side. So that's one of the isomers. The other one would look a little something like this. And I think you can convince yourself those two molecules are different, and there's no way to convert one into the other. So they're permanently different. Welcome to stereoisomers. And I've given the definition of stereoisomers in the class notes. We'll talk about it in several future classes also. But stereoisomers are molecules that have not just the same formula, but they also have the same connectivity. So they're not structural isomers. They're not constitutional isomers, because everything's connected the same. You have all the same types of bonds, but the atoms are arranged differently in 3-dimensional space, permanently. And I think you'll agree with me that those 2 methyl groups are on the same side of the 5-membered ring. So we'll say that they are cis, and I'll write this down in a moment. These 2 are on opposite sides, and so we'll say that they are trans. So this molecule, and again, you can practice naming cycloalkanes on your own. We'd have to call this one cis 1,3-dimethyl cyclopentane. And the other one we would have to call trans 1,3-dimethyl cyclopentane. Because they need different names. They're different molecules. We need to be able to distinguish them. And I think you'll see naming cycloalkanes is very similar to naming straight chain